Thank you, everybody, for joining today's ELISA seminar. Today, we're very delighted to have Stephen VanderLeest from the Boeing company and Zhang Wentao, a PhD student from the University of Illinois, Urbana-Champaign, to give us a talk on making Linux fly towards certified Linux kernel. Without further ado, I'm going to pass the microphone to Stephen and Zhang Wentao.
Very good. Thank you. Welcome, everyone. I see a number of friends and colleagues around the world have joined us. So glad that you're here to hear more about our project that Boeing is doing with University of Illinois. Let me jump right in. We're going to be covering some brief introductory material. I'm going to go over some of the needs and requirements that Boeing has for being able to use software in flight on aircraft where safety absolutely matters, and looking at some of the guidance for assuring the safety of software, and then focusing in on test coverage, one of the areas that we have some needs, and University of Illinois is helping us fill these gaps. So I'll end with kind of that motivation of the work, and then Wentao will take over and present the details of the research work he and his team have been doing, and some of the initial results. And then we'll wrap up with what the next steps are for us. Boeing, a worldwide company that you know designs and fields aircrafts commercially and for military aircraft. Boeing does also do other types of vehicles. So you'll find Boeing in space, under the sea, but you probably know us primarily for aircraft. I have spent my career in the aerospace industry in a variety of large and small companies, and I've been delighted to join Boeing working on this project, looking at how to use the open source Linux operating system at higher levels of criticality. Boeing and many others are already using Linux in many applications that are not safety critical, but trying to use it at those higher levels is really the goal of this project. University of Illinois is well known in computer science and computer engineering, and Wentao is part of a project under Professor Darko Marinov that is joining us on this work that Boeing is funding to look at enhancing an open source tool. We hope to get to a tool that we can use and actually qualify for use to demonstrate that the code has been thoroughly tested. You might be thinking, why should I be interested in this? The enhancements to the tool, we are open sourcing, and they're available. Wentao will give you some of that information in a little bit, so the enhanced coverage tool will be available to anyone to use. And all of us should be interested in better testing. So certainly in safety critical industries, like many of the participants in ELISA, absolutely need to do this. But even if you're not working with Linux in a safety critical domain, you're interested in its correctness. And so knowing it's correct in part is achieved by showing that we have thoroughly tested it and seen that it gives the expected results. Let's focus then on how aerospace thinks of it. The document DO-178C is a published standard that the FAA and many other civilian airworthiness organizations around the world point to say, here is how you demonstrate that your software is safe for use on an aircraft. It outlines 5 different levels of criticality. E being the least critical, so perhaps entertainment software or coffee maker software on the aircraft has no safety impact, all the way up to level A, which is if something goes wrong here, it's a catastrophic result. So you absolutely have to ensure at level A that the software is correct, that it's safe, that it's reliable. The standard lays out a number of objectives that must be met to demonstrate to the appropriate level of rigor that the software is correct. And you can see that the number of objectives goes up, with level A requiring all the objectives that the standard lays out to demonstrate that the software has been assured. The way that we do this is building up a set of evidence or artifacts that demonstrate that the software is correct. So at the very top of the chart here, you can see that we're developing system requirements describing what the software should be doing, what the expected behavior is. And we decompose that into finer and finer grained requirements, which are traced together, and so that you can see the traceability, the decomposition, and an architecture that describes the system, and then a set of tests which demonstrate that the software meets the requirements. Typically in safety critical industries like aerospace, you start from requirements and work your way down to the source code, developing it in stages. We're starting with the source code of Linux and then generating these artifacts around the source code. The focus for today's talk is on how we demonstrate that our set of tests exercising the source code meet requirements. And so one of the things we have to do then is show that the tests thoroughly exercise the source code. And at level A, it's a fairly refined type of coverage. Your target is that 100% of your software has been exercised. And at level A, or I should say the higher levels of assurance, you can't have any source code that you aren't demonstrating you need. So anything that's not being used is considered dead code and needs to be removed from the system, so that the only code flying on the aircraft is the code you've demonstrated that you have a requirement for and that it meets those requirements. So I mentioned there's those objectives that need to be met, 71 of them for level A. Here's 3 of them from the standard that are specifically about coverage. And I'm going to start at the bottom. This objective 7 from table 8F7 of the standard requires statement coverage. So if you're at criticality C, then you have to show that each statement in your source code has been executed by at least one of your tests. If you're at level B, this objective 6 is also necessary. You have to show that each decision takes all the values. You have to show that a decision went, for example, in an if-else, you have to show that you've exercised the if and the else part of the structure. And then at level A, we have to show that within a decision, each condition within the decision independently affects the outcome. So if you have a Boolean construct, you have to show that each of the elements there are independently affecting the decision. So you can see it's finer and finer grained coverage to say, have we tried the software in every way that it might be executed in operation and ensured that we're getting the expected result? So just a real quick, simple example. Here's a silly little program on the left that I just wrote as an example. And here's my test input. I'm going to call this function with the values 3 and 5. And you can see that that's going to drop down. It's going to evaluate this if, and that's going to evaluate true. So I'm going to evaluate this little sum statement and then return it. This test, a single test, gives me statement coverage. So I'd be good for level C with this test. If I want level B, I need to show that I evaluated this decision both true and false. So now I need 2 tests to get decision coverage. And if I want MCDC coverage, modified condition decision coverage, now I have to show that this first part and the second part of the condition independently affect whether I take the if. So now I have 3 tests to get to MCDC coverage. Each is a type of coverage, but at level A, I need that most fine-grained type of coverage. So there are commercial tools that will do these types of coverage, but they're primarily targeted at application software. It turns out that they are not well suited for testing the operating system itself. It can be done, but it takes some additional effort. And we were interested, since we were using the open source Linux operating system as our target, we also wanted open source tools that could do the coverage we need and in a qualified manner and on an operating system type of software. There were 2 choices that we looked at, gcov and LVMcov. They both can work with Linux kernel. And we decided to work on LVMcov as the tool that we're going to enhance. It already did a statement coverage. You can get a form of the decision coverage with LVM-COV. And there was some work beginning already on MCDC coverage. And that's what this project was about, to continue and expand on that work. So Boeing and University of Illinois at Urbana-Champaign have been collaborating to enhance LVM-COV. And it turns out there's some additional work that's coming. Wentao will hint at that a little bit. And you'll more in the future that there's some potential changes to the kernel itself that are necessary to collect some of the instrumentation we need in order to hit that highest level of criticality. So I will turn it over to Wentao then to present some of the details of the work we've been doing and our initial results.
All right, thanks, Steve, for making this nice introduction. Can everyone see the screen?
Yeah, we can see you.
Yeah. Okay, my name is Wentao. I'm a first-year PhD student at University of Illinois. Next, I will talk more about the technical details of our work, that is certifying Linux kernel and making it fly. So in order to do so, as mentioned by Steve, we have to meet all these objectives listed in the DO-178C standard, which means we must be able to measure Linux kernel's coverage from using the most basic metrics like statement coverage to using more advanced ones like data control coupling coverage or modified condition decision coverage. What we have been working on is this Objective 5 MCDC. Here, I also want to clarify that this work is enabling the measurement of MCDC, but improving the kernel coverage is just one of our next steps. At a certain stage in the future, we can probably apply all kinds of kernel testing techniques and come up with better strategies in order to achieve that goal. And here's the technical overview. In short, we have built the first infrastructure for measuring Linux kernel's MCDC based on open source solutions. Our infrastructure has three key components. First and foremost, we use clone/LLVM to compile and instrument the target kernel. Second, as for the target, we have been mostly experimenting with Linux version 5.15, but of course, we have also tested against either older versions or newer versions. And third, in order to cover a certain portion of the target code, we exercise some of the kernel testing techniques like KUnit and the K-self-test. And having all these components, the overall workflow is illustrated in this diagram, including 4 steps. First, we compile and instrument the target kernel. Then we boot it in QEMU. Next, within the virtual machine, we run some tests. And finally, we dump the profiles and generate the coverage reports. Let's look at the results. For example, this screenshot is the summary page of Linux kernel's coverage report. And in the rightmost column, we are able to read this MCDC statistics for the first time of Linux kernel, in addition to all those traditional coverage metrics. And in the bottom row, we also have these total numbers. I will talk more about them later. Here, I want to point out that this is just some initial experiments. So in general, the numbers are quite low, but it does open up the opportunity for future improvement in a more guided fashion. We can also dive into specific code locations and inspect the details. This example comes from this kernel/softirq.c. At line 415.8, we have this simple decision consisting of 2 conditions connected by a logical AND operator. And as the results suggest, one of the 2 condition pairs is covered, so the overall MCDC is 50%. Here we have another more complicated example that has 6 conditions connected by a series of OR operators and AND operators. And in this case, all 6 condition pairs are indeed covered. So for this decision, the overall coverage is 100%. So are you curious how we are able to get all this information? After seeing some of the coverage results, I think it will be good to explain a little bit of its internals. And here is an illustration. So in order to measure any kind of coverage, the compiler will have to assign all sorts of coverage mapping regions and the counters to the input source code. Let's take this program on the left-hand side as an example. All of its coverage mapping regions can be dumped using these compiler flags, and I will walk you through them one by one. In the first entry, we have a code region corresponding to the code block within the curly braces, and the toolchain will have to keep track of how many times this curly brace is entered. And second, we have another code region that corresponds to this decision of the if statement. And similarly, the toolchain will record how many times this decision is evaluated. And this is the same case for the first operand of this logical AND operator, as well as the second operand. And beyond that, at the same locations, we have another type of coverage mapping region called branch region. And for each of these branch regions, more information is being monitored. Specifically, the toolchain will have to keep track both how many times the true outcome is evaluated and how many times the false outcome is evaluated. And next, we have this second branch region corresponding to the later half of this decision. And the input program is instrumented in such a way so that eventually we can make sense of condition coverage or so-called branch coverage. And moving forward, we have more code regions. This one corresponding to the first return statement, and next one corresponding to the final return statement. After going over this whole program, some of you may have noticed that not all of these counters are actually independent with each other, and that's true. And the compiler is smart enough to only maintain 4 of them, that is #0, 1, 2, and 3, as highlighted in this blue font. And all the rest can be evaluated from these 4, either by subtraction or identity. So the only remaining step is to actually insert some code to the input program. And this is how these counters look like after being translated into intermediate representation or assembly code. They are essentially a sequence of 3 instructions. So first, it reads the counter value from the memory and increments it by 1. And lastly, it writes this information back to the memory. So putting everything together with all these instrumented coverage mapping regions and counters, it is possible for us to calculate the coverage of programs under test. After briefly introducing the internals of instrumentation and coverage measurement, I'd like to introduce the 3 components of our infrastructure, specifically the tool chain, our kernel support, as well as the test suite. As for the tool chain, we are using clone/LLVM, whose MCDC feature were merged into mainline just this January. And their implementation is built on top of Clon's own coverage mechanism called source-based code coverage, which is different from GCOV. And unlike some of the traditional coverage metrics, which utilize scalar counters, just as illustrated earlier, MCDC additionally requires bitmaps in order to track all the test vectors. And 2 months ago, we have the first official release of LLVM with all the MCDC functionality included. And even though most of the MCDC features have already been merged, they are still in a very early stage. That's why we want to make sure that the tools can work correctly and reliably. So we have been actively testing and verifying it in collaboration with the upstream. So far, we have contributed more than 3 PRs and reported a few other issues, as shown in this picture. Among all these bug reports and bug fixes, I'd like to highlight 2 of them, both of which were uncovered during our experiences of instrumenting Linux kernel, which is arguably a very unique target considering all its complex code patterns and unusual coding styles. In the first example, we hit some problems when dealing with this non-standard C syntax called statement expression, which essentially allows us to return a value within the code block and assign it to some variables. And the second example involves a complicated macro that uses this token concatenation syntax in order to form some new variable names or new function names. When we encounter this problem, we investigated them, reported them to the open source community, and even contributed our own solutions. So it's such a good news that we can have an open source tool to measure MCDC, but the fact is, even with all these bug fixes, it does not work out of the box for Linux kernel or any operating system kernel. The problem is, that's why we will need the corresponding kernel support. The problem is we need some way of exporting those in-memory counters and bitmaps so that we can calculate the coverage after all. This task is straightforward in user space because we can simply create a new file at the same directory as the executable and write that information into it. But in kernel space, it is a bit trickier because there's no such concept as current directory or parent directory. So instead, we need to write to a pseudo file system. And this exact piece of code is still missing there in the kernel. So in order to fill this gap, we make use of an early patch contributed by Google, and we implement the necessary functionality and put much more emphasis on the coverage measurement rather than performance profiling. And in this way, we make Linux kernel compatible with our coverage tools. We also plan to send this patch to the upstream so that a larger community can be benefited. And to further validate this kernel patch and to expose potential toolchain bugs, we have applied our infrastructure to many more kernel versions. The versions we are choosing are the 9 branches from the earliest long-term support to relatively newer stable branches up till the latest mainline. And the configuration we're using is a relatively small one taken from our university's operating systems class, and the results are shown in this table. As we can see, for 7 out of the 9 versions, the whole workflow can work successfully from end to end without hitting any warning or error, which makes us more confident that this kernel patch is indeed generalizable across kernel versions. We did hit a warning for these 2 stable branches, but even in these 2 cases, we were still able to generate the valid coverage report. But we will definitely continue investigating these 2 cases as we've done many times before. And finally, I'd like to talk about the third component of our infrastructure, that is the test suite. Essentially, we are conducting a few parallel experiments. In the first row, we only boot the kernel and immediately exit the virtual machine. And in the second, we additionally run some K-unit tests during the booting process. And in the third group, we further include K-self test. As indicated by this table, within the covered portion of kernel code, the booting process alone already contributes more than half of it. And the improvement introduced by K-unit doesn't look pretty much. And on the other hand, K self-test seems a bit more promising in improving kernel's coverage. So in general, these numbers are relatively low, and such result calls for more attention in this direction. And our work provides a good infrastructure to guide such future effort. In fact, one of our own next steps is to try even more test suites like ALTP Linux testing project, or combine with some fuzzing testing techniques.
And Wentao, I want to highlight while you're on this chart, it's not surprising that MCDC is low. No one has ever measured it before. This is the first time that, to my knowledge, someone has actually tried some of the standard test suites and looked at what is the MCDC coverage. So this wasn't a surprising result to us, but now we're making a tool available so anyone can go check how am I doing there to see what is that very fine-grained coverage. And we hope that by making the test available, that'll make it easier for people to contribute additional tests for better coverage.
Yep. All right. So actually, I have finished most of the contents of the slides. So next, let me demonstrate in practice how we can use our infrastructure to measure Linux kernel's MCDC. All right. So let's first look at the outline, which is consistent with what we've seen on the slides. Essentially, we will first prepare all the dependencies and the tool chain. Then we use them to build the Linux kernel. And then we boot it, run some tests, and finally, we connect the coverage and the generated reports. On the right-hand side, I have a demo machine, which is a fresh installation of Ubuntu 22. On this machine, I have already run the workflow a few times so that many steps later can be finished sooner. So as the first step, let's install some dependencies from our distro's package manager. Here, I group all these dependencies according to their purposes. For example, if we want to build LLVM from source, we will need some modern build systems and a more efficient linker. And this second group is the typical requirements of building a Linux kernel. And third, we also install QEMU, which will be used to boot the kernel we've just built. Additionally, in order to launch the virtual machines, we have to assign proper permission bits to this KVM device. And on my demo machine, it should have been done. All right, so the second step is to pull the needed source code and apply some patches. Here we have 3 repositories. The first, enhance-gconf, which is what we are looking at here exactly. It is a meta repository containing all the documentation, configuration files, scripts, etc. And the second, LLVM project, it's a collection of tools, and we will rely on the compiler and the coverage tools in it. And third, of course, is our target Linux kernel. As I said, we have been mostly experimenting with Linux 5.15, but we've also tested against other versions, either older or newer. So after obtaining this unmodified upstream source code, we need to apply some patches as well. As I said, for the Linux kernel, we have to implement the corresponding pseudo file system support as shown in these commits. And most of the changes reside under this kernel/clone profile directory. And as for LLVM, even though most of its MCDC features have already been merged, our local patch, on the other hand, includes some further improvement, adding more information to the final report. So with all these components ready, let's start building something. First, we're gonna build clone and LLVM. Normally, it would take a much longer time than what's demonstrated here because I've already built it before. So alternatively, you can also follow these instructions to download some nightly pre-built packages in order to save some time. Now the toolchain has been set up, so let's just build a kernel. So we will first download a base configuration file from our university's operating system class website, and we further enables these two options related to KUnit. As for the remaining steps of configuration, let me demonstrate more carefully and more explicitly. So let's first enter this menu configure mode of kernel configuration, and we search for keywords instru_profile, and we can easily locate the options added by our patch. And let's just enable them one by one. So by the first two, we enable Clon's own coverage mechanism called source-based code coverage, aka ACC. And the third one is exactly what we want, that is enabling kernel's MCDC measurement. Let's save this configuration file and start building. Again, it will be a quick incremental build, but what's happening under the hood is we append those MCDC compiler flags to every applicable compiler invocation so that we will end up with a Linux kernel that is instrumented with MCDC. Now, since the kernel is ready, what we have to do is just boot it in a virtual machine. And during this process, some KUnit tests are also executed as shown in this screen because we simply enable those two options. And now we should have entered the guest machine. So hopefully we should find the profile that we want in the debug sudo file system under C's kernel debug and under the directory created by our patch called clone instru profile and named after profile row. Here it is. It's just a bunch of binary file. Is a bunch of binary data. Let's move this file outside the virtual machine so that we can continue our workflow on the host environment. So maybe we can have better performance. And exit the virtual machine. We're back to the host, and we should have this exact same file. We can even run file command against it, and it's correctly recognized as LLVM row profile data. And the remaining step is actually similar to what we will do against user space program. Essentially, we first run this LLVM prof data to index and merge this profile row into a profile data. Then we run this whole thing to conduct the final analysis and the visualization. Let me actually navigate to this directory with the browser. So after that command finishes, the results will be put under a directory looking like this. But before it finishes, let's look at some of the previous runs. Clicking into these links, we can see the summary page for the whole Linux source tree with this specific column for MCDC. We can also follow these links and go to specific code locations. For example, here we have a simple decision that is 15% covered. Right. So apparently it needs a bit more time to finish. On my setup, it usually takes 1 to 2 minutes, but so far I have already demonstrated the whole process of measuring Linux kernel's MCDC. So, in summary, we are able to measure MCDC of Linux kernel for the first time using Clone LLVM18, and we have tested with many kernel versions. As the next steps, we will continue testing and improving the tools, especially reasoning about the accuracy of the reported data. We also want to promote our kernel patch to the upstream so that a larger community can be benefited. For the last three bullets, Steve can please elaborate on them and share some insights from the perspective of aviation industry. Steve, please.
Yeah, thanks, Wentao. So our next steps are actually looking at some of the other objectives from DO-178. Two of the rows that I didn't show you were some additional types of coverage. And so we'll be working with the University of Illinois in the coming year to tackle these additional types of coverage and add those, we hope, to the LLVM Cov tool. And this last bullet, actually, a couple of you were kind of asking in the chat and the questions, getting at this point, how do we know we can trust the tool? DO-178C actually says that if you are depending on a tool to replace human analysis, for example, checking the coverage, then you need to show that the tool is trustworthy, and you have to apply some of the same thinking, some of the same assurance to the tool itself. So we have a team within Boeing that's actually starting on this work, working just behind the development that the University of Illinois is doing to demonstrate that the tool is correct. And so there's a standard called DO-330, which for the aerospace industry guides how you would qualify the tool and demonstrate its correctness. And the basic idea would be generating some test cases for which you know the coverage answer and checking that the tool produces that. So the University of Illinois team already has a number of these tests as they've been doing the development. Our qualification team will augment that to say, here are all the different sorts of source code that you might instrument and the different tests you might use to execute that source code. And then here are the answers that you would expect. So in these cases, the tool qualification will actually, you have to demonstrate test cases and some sample source code. So that qual doesn't actually then work on the kernel. It's working on known examples so that you know when you do instrument the kernel that you're getting valid results back, that we can trust those results. So that work is ongoing as well. Most of the items you see here on this future work, we hope to have some future presentations coming back and saying, here's our progress. And in the meantime, we hope that you'll go give it a try. We've upstreamed the initial work. As Wentao said, these are our early days. So we're expecting that there's going to be some additional features needed. We may find some additional bugs either in the tool, or we might tease out bugs that we find in the kernel itself. That's part of the testing approach to say, is there some usage that's never been tried before that is not producing the expected result? And then I also want to just follow up with another question that was on the chat. Shouldn't you also check that the tests are producing the correct answers? Yes, absolutely. The focus of the coverage tool is whether your tests are exercising all of the code. Whether it's exercising it correctly, of course, we also need to check. So that is kind of to the side on our project. That's another stage that you would need to do to show the safety of the software. Our focus is on, do you have enough tests? Are they exercising everything in the code? And then, yes, you would couple that with, are you getting the answers that you expect? And then what are your expected answers? Well, those are tied to your requirements. So what is it you need the system to do? And is it doing that correctly? Part of the coverage is also checking kind of the reverse. So if you think of reliability as the property that the system produces the expected behavior, it's also checking the property of safety. The system does not produce any unexpected behavior. One of the ways you can get unexpected behavior is code that doesn't belong there, that's not being exercised for the requirements. Coverage tools catch that. If there's a chunk of code that's not being exercised by any of your tests, and you've fulfilled all your requirements, that's unnecessary code. And it might be benign. It just is code that you didn't have a need for, but it could also be it's a bug or even something malicious, that there's something there that shouldn't be there. And code coverage helps you tease out at least candidates that you have to consider. Why is this not being exercised? Am I missing a test? Is it something I don't need that I should take out? Is it going to cause a problem? So this tool is part of a larger, set of tools that we need to bring to bear to really demonstrate the software is safe and reliable. But it's a key piece of the puzzle, and one that we think now, we are approaching having an open source tool available that everyone can use to check, this very refined type of coverage. Let us know if you have other questions. We've got a few minutes here. I see a couple popping up, so maybe we'll just cover them live. Daniel says, how does Boeing plan to go from knowing the gap to filling the gap, considering the coverage? Great question. We internally, of course, have requirements for our particular systems, hundreds of different platforms, each with their own set of requirements that we, ourselves inside Boeing will say, how are we meeting those? But there's this larger open source community project to develop better testing of the kernel in general. And so Wentao mentioned some of the test suites that we've already been working with and some that we hope to use. We hope this contribution of a better tool will encourage people to add more tests. And so we see that as a community project as well, that we all should be adding to the test suites to provide more thorough testing. So we'd love to see getting from these, single digit or low double digit coverages up into, much closer to 100% coverage. And probably what you're going to have is the open source community will be contributing to these test suites, getting us to a fairly high number. And then it's probably going to have to be coupled with individual companies with their specific systems, adding their requirements and their specific tests to get you all the way to 100%. And I should mention, often there's some code that you just can't produce tests to execute. For example, defensive code might be there and you're never expecting to get to that code. But if something goes wrong in an unexpected way, you've got some defensive code, and that's code that you might not ever achieve full coverage for, at least in the aerospace industry. You then would document a justification for why your tests don't hit that particular chunk. All right, Andrew asked, do you expect this approach would work to collect SCA results on a target system environment as compared to QEMU? Oh, yeah, great question. Currently, the University of Illinois project is using, yes, an emulated approach. Ultimately, yeah, you'd want to be able to run on actual target hardware. There are certain tests that you only really can run on the hardware itself. So that is something we'll have to be considering going forward. The basic concept is applicable in that you instrument, collect the data, and analyze it. Wentao, do you want to add anything to that? There's nothing conceptually in the way of us collecting instrumentation even from on target, right?
So, yeah, there's no essential difference when you run all this workflow on a physical machine compared to virtual machine. Yeah. Here we use virtualized technology mostly because it can provide some sort of isolation from your host environment so that we can conduct our experiments more massively and more flexibly. That's the major concern. But we do believe this approach should work on physical machine on site. Yeah.
Great. Paul asks, are the results and documentation for this available somewhere in the open already? The initial enhancements to add MCDC have been upstreamed, as Wentao mentioned. These test results we're making public here. This webinar is being recorded as well, so those are available. The documentation, we probably have to think about where to add more public information on documentation. As you've heard, the project is sort of midstream. There's more work we're planning to do. But yeah, hold us accountable there to make sure that we are providing sufficient information for folks to use the tool and understand how to use it and what results get out of it. So yeah, more to come there. Great question.
Yeah, We plan to send out the kernel patch very soon. And right now we're doing more rounds of revision internally. And hopefully we can see that in the kernel mailing list in a short time.
Andrew asks, have you experimented with any sort of limitations on number of MCDC conditions? In a single expression, you can instrument some historians have had limits. Wentao, you want to answer that one?
Yeah, that's a good question. Actually, one of the current limitation of LLVM tool is that it can only support 2 to 6 condition within one decision. Because of the reason that you mentioned, it uses some bitmaps, and when the number of condition grows, the needed space within memory is growing exponentially. So it currently cannot support. But I learned from the upstream there is some effort to loosen this limit, and we hope it can be improved very soon. I also want to, yeah, please.
That is an important question, because that limitation of no more than 6 conditions is a problem for the kernel. There are condition statements that have well more than 6 conditions. One of the early investigations in this project was to check, and I think we found even one case where there's like 30 independent conditions in a single if. For at least for our purposes at Boeing, we will be running a profile of the kernel, not the entire source code, because at level A, you only want what's necessary there. So we think some of those very large condition statements might not end up being in our safety critical profile. Even so, that's still work in progress, and we want to expand the availability. It's very likely we'll need to do more than 6. Hopefully not as many as 30. We'll see. Wentao, you're going to add something?
I think that's all. Yeah.
Yeah. Okay. Great questions. Anything else? Igor asks, how do you manage the correlation between source code and optimized code the LLVM can produce, both on and LTO? Oh, great question. This actually gets at one of those objectives. It's the second to last bullet here, DO-178 objective 9. If you're doing anything under level A, so B or lower, it is sufficient to show that you've instrumented the source code and checked the coverage there. But what you're getting at is the executable object code doesn't actually always match exactly your source code because of optimization, or even without optimization. Sometimes the compiler or the linker will add some things that make it slightly different than the source code itself. Level A actually requires that you're looking at this. So one of the things that we're working on in the coming year is object coverage. That is actually checking the coverage within the executable object code itself, which includes then anything the compiler or the linker might have changed so that you're not exactly aligning with the source code. And so that is one of the really challenging areas that we're going to be tackling next, is can we connect it with object coverage itself? And then tying that back to the source code gets tricky, because you've got your object code coverage result, presumably if we are successful here, but then understanding how to improve your tests in order to achieve the 100% coverage, and hopefully looking at the source code will be an interesting challenge. In the end, you might have to literally look at the object code, because those differences might be something that the compiler has added in, especially with optimization. Sometimes in the aerospace industry, at least, we don't turn on any optimization because of this problem. And so you turn off optimization so that your source code does map more directly to object code. For the Linux kernel, for performance reasons, we may need to at least have sort of the typical optimization turned on. And if so, we definitely need this object coverage. Wentao, you want to add anything to that?
Yeah, so the general practice of measuring coverage, we usually turn off that optimization to get a more accurate result, accurate mapping back to the source code. But for Linux kernel, as Steve mentioned, there's no way to disable optimization entirely, so we must address this issue from the objective coverage perspective. Yeah.
Good. Matt Weber, thank you for this question. If there are further questions or discussion, where could one go? And so ELISA is hosting this webinar. There are 2 working groups that should be of interest if this topic's of interesting to you. There's an aerospace working group that's focused on what are the use cases, needs, and requirements for the aerospace industry specifically. There's also a tools working group that's specifically looking at what are the tools that can help any of the safety critical industries. ELISA also has people that are interested in medical devices. There's a working group for that. And automotive, there's a working group for that. And of course, there's other safety industries, rail, nuclear industry. You're all welcome to join in the conversations in the various ELISA working groups. So please check it out. If you go to the ELISA website, you can find the different working groups there and see the calendar of their meetings. Thanks, Matt, for mentioning that. And Min posted the link there. Okay, we're coming close to the hour here. Any other questions you want us to tackle today? These are all great questions, things that we've been thinking about and struggling with throughout the project. So it's great to hear you probing at those things. We welcome it. We want to make sure this tool is good for everyone and it has considered all the different challenges. Which is partly why we want it to be open source, so that we together collectively are improving the tool and making sure it's useful to all. All right, Min, I think that was the end of the questions. Looks like. Any closing words?
No, yeah, thank you very much for that very engaging talk, and thank you for to the participants for your questions and interactions on chat and Q&A. If we don't have any other questions, I am gonna stop the recording in a second.